To thank the organizers for this great conference, inviting me to it. It's been great so far. And also let me say I'm now proud to say I'm at University of California, Irvine now. So very proud to say so. Okay, that's okay. Princeton before that. Okay, so the title of my talk is Geometric Flows in Complex Geometry. And it is everything I'll talk about is joint work with Gang Tian. Okay, so given that this is the title, I should start by talking about the sort of fountainhead of geometric flows in complex geometry, which is Caylor-Ricci flow. So here the setup is I've got a two-n-dimensional manifold, a metric, and a complex structure, J. So J is an honest complex structure, so the Nine-Haus tensor vanishes. And so associated to, and also I have G is Hermitian, so J dot is G dot dot. And so associated to this I have the Kähler form omega dot dot is J dot dot. And then the all-important Kähler condition is that d omega is 0. So I just review these basic definitions because we're going to change them soon. So in this situation, one has the flow, which you can write in terms of the Kähler form as follows. So d omega dt is root minus 1 over 2 dd bar log determinant g, where really this is just the sort of typical shorthand for the representative of the first term class with respect to this complex manifold. And of course this is completely equivalent. This is exactly the same as the usual Ricci flow, minus 2 Ricci. So at this point the Kähler-Ricci flow has a very well-developed theory, some very deep results. And let me just mention kind of two of the most salient aspects of this theory for what I'm going to talk about. So one is there's an interesting connection to mathematical physics. In particular, of course, the steady points are Calabi-Yau manifolds, or more generally Kähler-Einstein, I guess, which have seen use in string theory, of course. And secondly, most importantly to what I'm going to talk about, the Perelman functionals, which have been so useful in understanding this equation, are somehow related to this physical so-called renormalization group flow. So I'll say a little bit more about what this is later. The point is somehow, he even mentions in his paper that somehow this viewpoint of this physical RG flow is somehow what inspired him to define some of his functionals. The second fantastic part of Kähler-Ricci flow is that there's a very precise existence criteria. And this is the following theorem of Tian and Zhang, which goes like this. So I start with a given Kähler manifold. And I guess I'll write the Kähler form maybe instead of the metric. So this is Kähler, and we let script K be the Kähler cone, which is the set of classes in H11 such that there exists F phi plus I dd bar F positive. So it's just classes which admit Kähler metrics. And then so we let T be the supremum of the set of T such that the initial Kähler class minus T times C1, first term class, is in K. So what you observe is that, this this capital T immediately, obviously, is the maximal time the flow could possibly exist. Because associated to a solution of Caylor-Ricci flow is an ODE in K. So the metric stays Kähler, and so you have this closed form varying in time in the Kähler cone. And basically, this is the time when the ODE hits the boundary of the Kähler cone. And so T is somehow the maximal time the flow could possibly exist. And then the theorem says, in fact, it does exist up to that time. So the implication is the solution to Kähler-Ricci flow exists on 0T. Okay? So very, very, very roughly, I mean, what's kind of amazing about this theorem is this sort of ODE implies PDE. I mean, you just have to check, you just sort of have to understand this ODE and this scalar cone to say how long the flow is going to exist. And what's more, I mean, it's possible to characterize this Kähler cone in terms of, say, how the Kähler form pairs against certain subvarieties. So you already have a guess. If you know sort of why you hit the boundary of the cone, you already have a guess as to what the singularity is. For instance, the typical example of a finite time singularity is like say on a Kähler surface is like contraction of a -1 curve, like contraction of some exceptional curve. So I mean, kind of in contrast to the story of Ricci flow on three manifolds is of course very well known, very beautiful. And there, of course, you can say what all the singularities are, but here somehow, I mean, the situation is even better. Like you, just given an initial cohomology class, you know exactly when the first singularity is going to occur. And there's already a good guess as to what the singularity is. And many precise results now exist about, for instance, showing that exceptional curves collapse under Kähler-Ricci flow. But that's a bit much for now. So the basic question that has driven my collaboration with Professor Tian is, can we extend aspects of this very nice theory to sort of less integrable situations? So there are many interesting geometric and topological questions on complex non-Kähler manifolds. And it would be nice to apply, I mean, given how great sort of the Kähler-Ricci flow is, it would be great to try to find some flows in situations that are less integrable. Okay, so I'm going to talk about one such flow. And so let me just start by giving you the following definition. So I mean, we want to weaken the Kähler condition, but we don't want to go too far. I mean, if we hope to preserve some of the nice results here. So we say M2N omega J is pluriclosed if dd bar omega equals 0. And this also goes under the name in the literature of strong Kähler with torsion. But I don't know, I just prefer one word. But anyways, it also goes by this name. Somehow, I mean, yeah, once you're going to leave the sort of perfect Kähler world, there are many different sort of conditions one can try to impose on omega. But in a sense, this is sort of the only non-trivial linear condition to impose, at least if you're going to keep J integrable. Okay, and the first theorem I have to mention, this is a theorem of Gaugushon, is given M2N omega J, just a Hermitian manifold, there exists a unique U smooth function such that the integral of U is 0 and dd bar of e to the 2u omega to the n minus first power is 0. So he solves a conformal deformation problem to solve this condition. And so the upshot for us is that every complex surface admits pluriclosed metrics. Okay, so that's just n equals 2, right? It's just n equals 2. And moreover, they're unique in a conformal class. So, right. So, as it turns out, there is a flow which preserves this condition. And at first, I'm just going to write it down. So here it is. This is this pluriclosed flow. It looks like this. So d omega dt is del star omega plus del bar star omega plus the first term class term. Okay? So, so we first, we discovered this purely from a pretty naive standpoint of just looking for a parabolic equation in this setting. But in the rest of the talk, I want to show you there's really a huge amount of geometry going on in this. That's what I'm going to focus on today. But let me just write down the first theorem myself and Tien. So this is just the basic existence theorem. So given M2n omega j, or omega naught j, pluriclosed, there exists a unique solution to the pluriclosed flow, that would be PCF, on a maximal time interval zero t with initial condition omega naught. And moreover, if omega naught is scalar, the solution is that of Kähler-Ricci flow. So this is just sort of it's a direct generalization of Kähler-Ricci flow to this less integrable situation. So the whole game really is to understand, of course, what's happening at capital T. I mean, that's the whole game with these flows is to understand what's happening there. And of course, we do have, we can say quite a bit. I mean, we don't have, of course, the full story yet, but I'm not really I don't think I'll have time to really talk about that today. Maybe a little at the end. But I really just want to talk about two things in the rest of the time. So I'll discuss how we found the Perlman functionals for this flow, and then I want to talk about an optimal regularity conjecture analogous to the Tian-Zhang theorem, sort of an ODE implies PDE conjecture. And if there's time, I'll talk about the topological applications of this conjecture. So, these flows are hard to work with, and so, you better have a good reason to try to work so hard to get some estimates. And so, we started this story looking for this specifically to try to understand the classification of complex non-Kähler surfaces, which has remained open for a long time now. And as it turns out, this pretty natural, well-motivated conjecture has something to say about this. So hopefully I'll get there by the end. Okay. But so for now, let me just talk about these Perlman functionals. So to do this, I have to take what appears to be a detour. But the kind of amazing part is it's not. So I want to give you a little a little introduction to the B field. We already had a fairly profound discussion of the B field in Professor Hitchens' talk, but I'm going to give you a very, very, very low-tech motivation for the B field. And I just want to start by I'm going to give it to you just by direct analogy with U1 Yang-Mills. I'm not even going to give the proper definition of U1 Yang-Mills. So here you can just think of the connection as take a locally defined one form, and then you have the field strength F is dA, and of course it's closed. That's immediate, and A is only locally defined, so of course F doesn't have to be null cohomologous. And then the field strength equations you try to solve for d star F equals 0. You try to solve for this Maxwell equation. Of course, in this case, it's pretty easy. But so motivated by some string theory that I don't understand, they introduced the B field. The physicists introduced this B field. So again, you can just take this pure low-tech analogy. So here B can just be a locally defined two form, and then you have a field strength H. So you just think of this as like a generalized magnetic field. H is dB, and again, it doesn't have to be null cohomologous. And H is of course closed. And when you attach sort of the energy of H, the L2 norm of H to some Lagrangian, you try to solve this sort of Maxwell type equation for your physical theory. Okay, so physicists introduced this B field and this sort of magnetic field H, and well, they attached, like I said, its energy to the Lagrangians, and they have this argument in string theory where they sort of look at the energy of maps of Riemann surfaces into some target space. The Riemann surface is supposed to represent the world sheet of a string. And you have some energy involving sort of the curvature of the target and H on the target. And then you try to impose consistency of the physics on different length scales, and out of it comes this certain evolution equation, which looks like this. So dg dt, I guess I use indices, ij, is minus 2 Ricci ij plus 1/2 hi pq hj pq, and then dh dt is the Laplace-Beltrami operator acting on h. So I mean the physical motivation is not really relevant for us. I'll just call this the B field renormalization group flow. And this, for instance, appears in Polchinski's string theory book. It's been around for a long time. And what's nice is sort of because it comes from this physical picture, there are direct analogies of the Perelman functionals for this flow. Sorry, let me not state the theorem yet. So for instance, one can define this functional script f, which takes a metric, a closed three-form h, and a function f, and gives you the integral r minus 1/12 norm h squared plus norm grad f squared e to minus f dv. So for those familiar with Ricci flow, you'll recognize this. This is just the Perelman's f functional modified with this extra term. And then lambda is the infimum over these unit volume f's of script f, fgf. And so again, this is the first eigenvalue of a certain Schrodinger operator associated to the metric and h. And then the theorem, there's a theorem of Oleinik, it's hard to spell, I think that's right. Well, Oleinik, Sunita, and Wolgar. which says that the B field RG flow is the gradient flow of lambda. Okay, this lambda. So this is in direct. Direct analogy with like the very first theorem in Perelman's first paper. So the first thing he shows is this energy functional with H0, and so they generalize it to this more general B field flow, and then furthermore, I'm not going to give the precise statement. It's not really. There's maybe not time for it, but so I gave. Let's put in quotes. An expanding entropy. So he also defined these, Perelman defined these expanding entropy for B field RG flow. I mean, the point is some parts of the rest of what Perelman did also generalized to this. But it's the precise statement we don't really need today. The point is you can do it. Okay, so why did I do this? Why did I take us down this road? Well, it's because of the following theorem. So here's the theorem of myself and Tien. So let n2n omega t j a solution to pluriclosed flow, and let x be the following vector field. So it's minus j d star omega, and then raise the index. And then let phi t be the diffeos generated by x. And then, sorry, there's still more. I don't want to erase this. And then finally, let h be dc omega, which by definition is minus d omega j. Okay, so I guess that's all the setup now, right? Yeah. Okay. And then the statement is that g of phi t star g of t phi t star h of t solves the B field flow. This one. Okay, so that's the theorem, and we were, I don't know, somehow the theorem it's just a calculation, but it very much depends on knowing the right calculation to do. I don't know, somehow it was not immediate to make this connection. I mean, there are many different ways to somehow look at the first order invariance, to somehow look at d omega, but in any case, there was a good reason to sort of set things up this way. But it turns out to be true. And so, of course, the consequence now is that this pluriclosed flow has these monotone functionals now. So we have these functionals now for this pluriclosed flow because, of course, they're diffeomorphism invariant. And so just modifying by diffeomorphisms, it doesn't change. I mean, you still get these monotone functionals. So it's an immediate consequence of this theorem. I mean, we were very surprised to see this. I mean, somehow this had been around for a long time, but we now have sort of a complex version of that flow. And while I'm here, I have to mention another consequence of this observation, which involves generalized Kähler geometry. So let me just first write down this system of equations. So here I have n2n Kähler form, and I have two integrable complex structures, j plus and minus. And then I impose the following conditions: dc plus omega plus, sorry, that's not the right way to write it. So, sorry, I have a metric and I have two complex structures, so I have two Kähler forms. And I impose the following conditions, and then dc plus minus omega plus minus equals 0. So basically what it is your metric is pluriclosed with respect to two distinct, well, possibly distinct complex structures. And moreover, their torsions are just negative of each other. And this system originally appeared in the work of Gates, Hull, and Rocek, and was later sort of given the proper geometric framework by Hitchin, Gualtieri, Cavalcanti, probably others also. But so they kind of gave the right way to look at these equations. And so another consequence of somehow that theorem, that observation, and I guess maybe in the interest of time I'll just write it in quotes. So this is again myself and Tian. So the B field flow preserves generalized Kähler geometry. The reason I put in quotes is because you just have to be careful about this gauge. So now there are two gauges actually. But if you just look at things in terms of like this flow, basically what's happening is your two complex structures are actually evolving by heat equations themselves. But if you look at it in terms of like the natural complex gauge of pluriclosed flow, of course, it's just, you just have to pull it back by the right diffeomorphism. But again, you now have two distinct pluriclosed structures. You can kind of look at it on the left side, the right side, or just the metric. But anyways, this is the bottom line is it does in fact preserve this structure. And again, I think it would be somehow very hard to guess this without already knowing this connection to the pluriclosed flow. Okay. So that will maybe be the end of the first part. And so I got 10 minutes. I'll talk about this conjectural regularity. Okay, so let me define, again, I've got, let's just maybe restrict to surfaces, although most of the discussion is general. I've got M4 omega J pluriclosed. And I can define the following cohomology group, which I call H11 del plus del bar. This is phi 11 forms, which are pluriclosed up to so-called like D plus D bar exact 1-1 forms. So alpha is a 0-1 form. Okay, so it's just a certain cohomology space, and in fact, one can just show that it's actually finite dimensional. And somehow you see that, I guess the equation is gone, but the pluriclosed flow naturally is a flow in this cohomology group, right? Because, let me just write it down again. So d omega dt is del star omega plus del bar star omega plus this closed term. So basically, as far as the cohomology group is concerned, this term is exact. And so it's in fact flowing somehow by the exact same ODE in this space as Kähler-Ricci flow. And so one can also define we call P11 del plus del bar, and this is just the set of classes in H11 which admit positive representatives such that there exists alpha phi plus d alpha plus d bar alpha bar is positive. So this is just direct analogy with the Kähler cone, right? I'm just looking at positive classes which admit metrics. And then so the conjecture that we make is, so given m2n omega j, or okay, I guess 4. That's fine. We'll just do surfaces. So given m4 omega j pluriclosed omega naught, we just let t be the supremum of times such that this remains, this is just the class at time t. So as long as the class remains in the positive cone, so it's this t, then we just conjecture the flow exists. Then the flow exists on 0t. So this is in, it's in direct analogy with this theorem of Tian and Zhang. It's just, there's kind of a natural cohomology space, there's a natural positive cone, so we make this conjecture. And let me just say a few words now about what this might imply, or it does imply, I guess. So we have the following theorem, which is that we can characterize this cone on surfaces. So this one definitely is very much four-dimensional. I don't know, everything up to this point it's all 2n-dimensional, but this is very much four-dimensional. So m2n omega j pluriclosed, and let's just say, so let phi be a 1-1 form, which is d bar closed, and then phi is in the positive cone. The class is in the positive cone if and only if the integral over m d wedge gamma naught is positive, and I'll define that in a second, and the integral over every curve of phi is positive for all irreducible effective divisors with d squared less or equal to 0. Okay, so let me just define this gamma naught. So gamma naught generates exact d alpha 1-1 form, where alpha is a 1 form, up to I dd bar f, where f is a smooth function. So gamma is measuring, gamma is measuring the failure of the dd bar lemma. Okay, so we're not in the Cayley situation anymore. So in the Cayley situation, of course, this is 0. That's exactly what the dd bar lemma says, right? Is that that's 0. But in this non-Cayley situation, it's no longer 0. But in fact, you can show it's one-dimensional. I mean, you can show it's one-dimensional, so you just let gamma naught be a generator which is positive in the sense of pairing positively against metrics. And so all you have to ask for general form is that it pair against gamma naught to be positive, and then it pairs positively against curves, and then in fact it's in the positive cone. So you can completely understand this cone in the case of complex surfaces. So in the last 5 minutes, I'm just going to say a word about these class 7 surfaces. So the definition is just it's a complex surface with B1 equal to 1. That's really all you need for the definition. And they remain unclassified, but there is a strongly motivated conjectural list. There's sort of a few families that are conjectured to be everything, conjectured to be all of these, but it's unknown whether it's actually true. And although I guess it's complete the classification is known for B2 equals 1, and at least topologically for B2 equals 2. This is due to Telemann using gauge theory, basically. Right. So there's a very nice theorem of Dluski, Oyaklas, and Thomas, which says that if I have M4J, B1 equals 1, B2 positive, if there exist B2 many rational curves, then M4J belongs to the known list. So just in a nutshell, it belongs to the known list. Oh, and I should have said, so at least this maybe looks very opaque, but it's really not so bad. So the conjectural list is that M4 is always diffeomorphic to S3 cross S1 connects some n copies of CP2 bar, where this n is giving you B2, of course. The topological, or even the smooth classification is quite simple. They should all just be this. But there's sort of a large family of possible complex structures one can put on this. Okay, but really the topological classification is not so crazy. The manifold should be pretty simple. And I'll just mention this Telemann proof uses this theorem also. So he uses gauge theory to find a curve in the case B2 equals 1, and something a little bit different when B2 equals 2. But basically the point is, like a lot of things in complex geometry, as long as you can find curves, the curves help you get classification results. So the very last thing I'll mention is one more theorem which kind of ties everything together. So the existence conjecture, which I guess I just erased, but the one that ended here. The existence conjecture about the ODE implies PDE statement. This implies the existence of at least one curve on these class 7 surfaces with B2 positive. So in particular, it would recover the classification when B2 equals 1. And in fact tell you something much stronger, that, all of these at least have one curve. And we hope to show that the existence conjecture implies all the curves, but we're still working on that. And maybe, just real quickly, the proof, just by sort of looking at the sort of cohomological properties of these class 7 surfaces, you can completely understand the ODE in the positive cone, and it sort of stays in it for all time. And even if you fix the volume of the flow, you still stay in the positive cone for all time. So basically what that's saying, what the conjecture then says, is that if I fix the volume of the flow, I have bounds on all the curvature and everything I would want. And then also, sort of by using the cohomological characteristics of these surfaces, you can show that the unnormalized solution to the flow is one of these, it's roughly an expanding solution. So just by a compactness argument, you can get the existence of an expanding breather, so-called expanding breather solution on this class 7 surface. And that's when these Paraman functionals intervene. And so using that, you can show that, in fact, it would be limiting to a Kähler-Einstein metric, which, of course, is impossible because these manifolds are explicitly non-Kähler. They admit no Kähler metrics at all. So that's sort of how the proof goes. And right, I should have said, the very first part saying that the volume normalized solution stays in the positive cone, that's only if there are no curves. So sorry, the first assumption is you say, assume there are no curves at all, then you stay in the positive cone. Of course, what we expect to happen is these curves eventually sort of collapse at time infinity, and that's how you leave the cone, and you get some sort of singular limit at the end. But that's still a work in progress. Okay, so thank you.